All right, I think that's probably good. So yeah, it's a pleasure to welcome today's lunch speaker, Aritra Ghosh. Aritra is a grad student at Yale, working with Meg Urey. His work focuses on the application of machine learning methods to understand the formation and evolution of galaxies and AGN. Some super interesting stuff, and he's going to tell us today about how to use those techniques to understand the morphology of very large numbers of galaxies from the Hyper Suprime-Cam survey. So over to you, Aritra.
Thank you so much, Andrew. And good morning / afternoon to everyone. Sorry I could not be in person, but I will be visiting Carnegie on October 19th. So hopefully I get a chance to meet some of you while I'm there. As Andrew said, I'm a graduate student at Yale, and I work largely on using machine learning techniques to study the formation and evolution of galaxies. And today, what I'll be telling all of you about is this new machine learning method that we have developed to determine the morphological parameters of galaxies and how we have applied this to the Hyper Suprime-Cam survey. So first, I am sure none of you probably need it, but I will start with a little bit of motivation of why we are interested in galaxy morphology. So as you all know, galaxies come in a very wide variety of shapes and sizes, but what does the morphology of a galaxy tell us about it? Now, for almost a century, starting with Hubble in 1926, astronomers have linked the morphology of galaxies to the physics of galaxy formation and evolution. Like morphology has been shown to be related to many fundamental properties of the galaxy as well as that of its environment. And this includes like mass, star formation rate, merger history, stellar kinematics, presence of supermassive black holes, and a host of other things. And although I don't have the time to go into each of these things to motivate my point, what I will do is I will kind of maybe talk a little bit about the merger history, for example. So as you can see in the simulation, you'll see two disk-dominated galaxies merging with each other. And as you can expect, what will happen at the end of this process is that the disk won't survive the merger, and at the end of the merger, you will end up with an elliptical galaxy. So the point being that morphology is interesting in its own right, of course, but it can also be used to trace other things. For example, if you see a disk-dominated galaxy in its current state, you can be pretty sure that it did not have a major merger in the recent past. On the other hand, if you see a bulge-dominated galaxy, then there's a certain chance that in the recent past, if it might have had a major merger. So essentially, the point being that you can use morphology to trace the merger history of galaxies and therefore identify galaxies on different evolutionary pathways. So that is the very broad reasoning of why we are interested in studying the morphology of galaxies. And as you might expect, in the last few years, in the last 5 or 6 years, as the sizes of large-scale optical surveys have grown, and also looking forward to the next decade of surveys, people have started using machine learning techniques to study the morphology of galaxies. And the term big data is something that is thrown around a lot, but sometimes it's helpful to actually look at the numbers. So it's interesting to talk about like how big will big data be in astronomy over the next decade. And the y-axis in this plot is logarithmic. And so essentially, roughly what you could argue is that we'll be producing about 100 times more data every night. And this is not true, but if you kind of give me a little bit of leeway, I could argue that to continue making inferences at the same rate, newer algorithms will need to reduce in one day the same data that older algorithms did in about 100 days or 3 months. So the question is then, can you do this with light profile fitting tools like GalFit, StatMorph, or citizen science projects like Galaxy Zoo? And thus, for very large scale morphology determination, I would argue that machine learning is not only an option, it is rather a necessity that all of us will have to use going into the next decade. But the question is, does that mean that this is the only tool to use? We should use it all the time? I don't think so. I think the algorithms that we'll be developing to study the morphology of galaxies, and actually most other things that we'll be using machine learning for, is complementary to other existing tools. And to make my point, I often like to think about what tool to best use in terms of this plot. So on the y-axis, you have the amount of customization that you want in your morphology determination algorithm. And on the x-axis, you have the number of galaxies. And here is where I see all the tools, basically. So essentially, if you want to have a limited number of galaxies and you want a lot of customization in how you want to determine your morphology, you want to add spiral arms, you want to add bending modes, and you want to add other things, then you can use a profile trading tool like GalFit, which allows you a lot of customization, but it's only practical to use it for a limited number of galaxies. On the other hand, with machine learning, if you are willing to give up some of that customization, then you can deal with a very large number of galaxies. And citizen science projects like Galaxy Zoo kind of fall somewhere in between these two. And I often find it helpful to also think about this in terms of this funnel approach. So essentially, you might start with very large amounts of data and pass through this funnel of machine learning, use it to identify specific subsamples of interest, and then reanalyze them in a more customized fashion. So this is kind of my view of how to see machine learning algorithms in morphology determination in view of other algorithms that are out there. Now, but wasn't there machine learning algorithms to determine morphology already? Why did we go ahead and build a new algorithm to determine the morphology of galaxies? And to answer that question, it's imperative to look at what previously has been done. So there has been a lot of work done on morphological classification using machine learning. So what that means is dividing of galaxies into broad classes of morphology as being disk dominated, bulge dominated, or having bars and these other things. But there has been very limited work done on estimating morphological parameters. And along with estimation of parameters comes the question of estimation of uncertainties. That are you able to estimate the uncertainties on the predicted parameters? And another challenge that has always been persistent in machine learning is the need for large pre-processed training sets. But this, of course, becomes a challenge if you want to apply your algorithm to a new survey, because for that, your training data does not exist. If you're going to use an algorithm to process a new survey, then it kind of becomes like a chicken and egg problem. You don't have the data to train it. Thus, how do you train an algorithm to tell you the answers? And the last being the need for fixed cutouts. So essentially, most machine learning algorithms, an issue is that it needs image cutouts of a fixed size. And what that often leads to is that you will have, if you have a wide range of galaxies with a range of magnitudes and masses, then for the smaller galaxies, you will often have secondary objects present in the cutout, and that often leads to spurious classifications. And I would argue all these points, and especially the first 2 points, are extremely important for deriving robust scaling relations and tests of theoretical models using morphology. That you need parameter estimations, and you need robust uncertainties. And in order to answer these challenges, we developed some machine learning tools to kind of address all these challenges and a few others. And there are 3 tools that I've worked on over the last few years. And they are called GAMONet, or Galaxy Morphology Network, GaMPEN, Galaxy Morphology Posterior Estimation Network, and PSF-CAM, which is a generative network slightly different from the other 2. And what each of them does is GAMONet determines morphological classifications of galaxies. GaMPEN tells you Bayesian posteriors for, that is, values and uncertainties for different morphological parameters. And what PSF-GAN does is it makes the above 2 algorithms also work on AGN host galaxies. As you might know or expect, it's slightly different to work with AGN host galaxies because the point source at the center can be very bright that it outshines almost the entire galaxy. So you need to take that point source out. So that's why we need a separate algorithm to do some pre-processing. And for today's talk, I will focus mostly on the second algorithm that we have developed called the Galaxy Morphology Posterior Estimation Network, or GaMPEN. But before I kind of jump into talking about this convolutional neural network, this machine learning algorithm, what I will do is I will spend about 5 minutes on kind of this very brief introduction to convolutional neural networks, because I don't like to use them in my talks as black boxes, because I don't think you should use them as black boxes. So let us take kind of a few moments to understand what it is. And for that, I want to do a little demo. So if you have a pen or paper near you, you should grab it, and I will kind of give you a little task. I'll ask you to draw something, and you'll have 20 seconds to draw. So it's a very simple challenge. You have to draw something from memory. I will tell you what you have to draw, and you'll have 20 seconds to draw it. So, okay, I will start. Hopefully many of you have your pens and papers. You will need to draw a bicycle. So go ahead. 15 seconds left. And we're 5, 3, 2, 1. Okay, stop. Now, if any of you would want to kind of hold up to the camera as your little bicycles, I would love to have a look at them. If you want to do that. Okay. Yeah. Okay, I see Andrew's bicycle. But I think what the thing is, and all of you have seen bicycles. You know how they look. You see how they are. And this is an actual bicycle. Now, when I usually do this, or when this has been done on larger scales as well, what is often seen is that when people are asked to draw a bicycle, they do draw 2 circles, and they draw a bunch of lines which connect the 2 circles. But they often don't get right the exact structure correct of those lines, like this. This exact triangle at the back and this triangle at the front. You often have lines. You might have lines connecting the 2 circles or something else. So the point being, like whenever I tell you to draw a bicycle, the multiple visual cortexes which are in your brain, which has hundreds of millions of neurons, that instantly kind of pops in your head, oh, I need to see 2 circles and some lines connecting. So what has happened over time is that our brains have learned a very efficient way to see information and store it in an abstract way. We let go of the minute details, but we keep the information about broad patterns or large-scale patterns. And artificial neural networks are absolutely nothing different, but just like our brains. So they have their collections of these different units, which we call artificial neurons. And all they do is that they transform high-level visual concepts into more like humanly readable formats of data. And it does so while filtering out irrelevant visual details. And to kind of explain this point a little bit more, you should think about artificial neurons, but I like to think of them as these devices which can help you take decisions. For example, let's say you want to decide whether you want to go to a restaurant or not. Now, there might be various factors which are involved in your decision, like how is the food quality? How is the quality of service? If you're worried about COVID, then what is the rate of test negativity in that area? And each of these inputs, which are determined by these X's over here, you might have different weights for each of these inputs. And then there's an inherent bias. That is how inherently likely are you to go to a restaurant. And that is what we call this bias. And essentially what you might then be able to do if you write out this function, which we call the sigmoid function, then you can plug in some numbers and then take a decision. So what artificial neurons are is that they help you take logical decisions based on input evidence. So you give a bunch of inputs to the data, to the model, to the neuron, it looks at it, it compares them at different levels and gives you an output. That is all what an individual neuron is. And when you combine a lot of these neurons, then you get neural networks. Now, the specific type of neural network that we use are convolutional neural networks. And what is a convolutional layer? A convolutional layer is nothing but it's trying to look for specific features in an image. And how they work is in this hierarchical framework where, for example, let's say I'm trying to use a convolutional neural network to understand whether there's an image of a cat or not. And if this is an input image, what the neural network usually looks for in the first few layers is very simple features like edges. So it detects the different edges in the image. And then it goes on to combine those things to ask the question, okay, is there an eye? Is there a nose? Is there a ear? And if all of these are present, then it says, okay, that's it. So it goes through this hierarchical decision making process. And how we detect these individual patterns is these things called filters. So what we usually do is slide this filter along the entire image, and that tells us whether a specific pattern is present in a specific portion of the image. And at the end of the day, what all these filters are just a bunch of numbers. So at the end of the day, you're taking your image, which is a matrix, you're multiplying it by a filter, which is again a matrix, and you're just sliding it around. So that is all there is to convolutional layers. It's basically these tools that we use to detect features in images. Now, I'm sure you might have seen examples of this cat image before, but how does the same image look when we work with galaxies? So this is what we have done is with our image classification network GaMRNet, on the left-hand side, you will see the shallower layers. And on the right-hand side, we have the deeper layers. And what they're showing you, these 4 boxes, are essentially randomly chosen filters that we have taken out from our networks. And we are trying to show you what are we trying to detect. So as you can see towards the left, which is more shallower layers, you see that the network is trying to look for very simple features like edges and lines and things like that. And as we go deeper and deeper into the network, by the point we have reached over here or here, the network is trying, at that point, it has understood that, okay, I need to look for these circles, and it's trying to focus on these galaxies. And as we move even deeper towards the last few layers here, as you can see, the network is trying to look for even sub-features in these galaxies, like these spiral arms and other things. So essentially, convolutional neural networks, they represent a hierarchical decision-making process where I'm initially looking for simple features. And as I go deeper and deeper into the network, I increasingly look for more complicated features. So that is your very brief introduction to convolutional neural networks. Now, let's talk about the specific convolutional neural network that we developed. It's called GaMPEN, or Galaxy Morphology Posterior Estimation Network. And what it does is that if you give an input image into GaMPEN, it has 2 parts. It first uses this thing called a Spatial Transformer Network to crop into the galaxy of interest at the center. It does so automatically, and I will explain on this in a little bit, without any human interaction into this. And then we use a downstream convolutional neural network to make posterior estimates of the galaxy's bulge-to-total light ratio, the effective radius, and the flux. Now, these 3 parameters, the bulge-to-total light ratio, effective radius, and flux, are not hard-coded into the network. We chose to predict these parameters for our work, but you can use this tool to predict any morphological parameters that you may want to use. Now, GaMPEN is also a rotation invariant deep learning framework. CNNs by design are not rotation invariant, but you usually have to induce rotational invariance in them. And to show it, what I will do is I will kind of get rid of these joint posteriors and just show you marginalized posteriors. And again, it's just bulge-to-total light ratio, effective radius, and flux. And what I will do now is I will just turn these galaxies. I will rotate these galaxies and show you the output. And as you can see, and the red kind of line kind of traces out by how much the mode of the predicted distributions vary. And as you can see, even when the galaxies rotate under rotations, the predictions are fairly stable. So essentially, they are pretty stable to different kinds of rotations. And as I already said, I will talk about these specific 3 parameters, but these are not hard-coded into the network. So next comes the question of what do we use GaMPEN for? What do we apply it on? So we choose to apply GaMPEN on images from the Hyper Suprime-Cam survey. And the question is why? To make that point, I kind of just easily compare it to SDSS, for example. Hyper Suprime-Cam allows us to probe fainter magnitudes and higher redshifts at better seeing and pixel scale compared to, for example, something like SDSS. And the specific sample that we chose to deal with is the Hyper Suprime-Cam wide survey, which is the biggest layer in Hyper Suprime-Cam. And we go up till a redshift 0.75. We go up till magnitude 23, which, as you can see, what I'm showing you over here is the current state of the art, as you could say, bulge disk decomposition catalog is the SIMART catalog. And if you just, if I show you the distribution of data in SIMART and distribution of our data, the primary thing that you're gaining is you can go out till higher redshifts and you can go out till fainter magnitude. So that's the new thing in this catalog, besides just the gain in sheer numbers that we have in terms of volume. So we have, as the table over here shows you, we have about 8 million galaxies. We have about 1 million in the lowest redshift bin and 3 and 4 million in the middle and the high redshift bins. And what we do here is we image, or we choose images in 3 different bands for each of these redshift bins. We choose G band imaging for the lowest redshift bin, R band for the middle redshift bin, and I band for the highest redshift bin. And the reason that we do this is, as this plot over here shows to you, to trace out roughly the same light in the rest frame. So if you take like 450 nanometers and see where it lies in each of these redshift bins, essentially you could say by using these 3 different filters, we're effectively tracing out something like 450 nanometers at each of these different redshifts. And that's the reason we choose to image in these 3 different bands for our 3 different galaxies. Now, what does the distribution of data look like for us? So what we have over here on the left is the redshift distribution of the galaxies. On the right is the magnitude distribution. And as you might expect, as we preferentially go towards higher redshifts, the fraction of objects which are at fainter magnitudes increases. But that's roughly just to give you an idea of what the distribution of data is in our sample. So that hopefully you now have an introduction to what our tool is and how does our sample look like. Next, let's talk a little bit about how does GaMPEN work. So I spoke to you about these this frame in this module in GaMPEN called the Spatial Transformer Network, which can automatically crop galaxies. Now, how does this work? So what I have over here is on the left, we have an input image. And when we feed it into this network, it gives us an automatically cropped output image. So what happens is that it passes through this convolutional neural network, the input image. And what it does is that it predicts the 6 parameters of an affine transformation. And based on this, it predicts such an affine transformation for each individual input galaxy. And then what we do is that we use a grid generator and a sampler to just apply this affine transformation on the input galaxy, ending up with our final output. And the network learns to make these predictions about these 6 parameters as it gets trained during the training process. But how do we train this thing? The best part about this, using this STN as we have used it in the framework, is that we use a differentiable transform. And what happens is that we just need one loss function. And the loss function that we have is just about optimizing the morphology. And the loss gradients from that loss function just can propagate all the way back into the STN. So essentially, the spatial transformer network, it just trains along with the CNN without any additional supervision. So you don't have to do anything else. You don't have to provide any additional, this is an example cutout of how a human would have done it. No, you just stick this into your framework. And with time, the STN learns to make crops because it's training with the same loss function. It learns to make transformations or croppings that is helpful in the downstream task of morphological classification. So that is how we train the STN. Now, how does the results look like? So here I'm showing you examples on the top row are from the images that we input into the spatial transformer network. And the bottom row is the outputs of these spatial transformer network images. As you can see in all these cases, all of these have secondary objects present in the frame. And using the STN, it helps us zoom in into the object of interest at the center, and it crops out most of these secondary objects which are present in the frame. So that's kind of the general use case of the spatial transformer network. But you may ask, okay, but how do we know? Is there some, we didn't ask it to do specific things, but is the spatial transformer network making different types of croppings for different kinds of galaxies? And it turns out, yes, that is indeed the case. The STN makes specific transformation for specific galaxies, and it learns to do it on its own. And to investigate this, what we did was we took all the cropped galaxies that we had in our dataset. We applied it on the entire dataset, of course, and then we ranked them based on the amount of cropping that the STN had done on these different galaxies. And on the left-hand side, I am showing you the 3 most aggressive crops. That is the maximum amount of cropping that it applied. And this is done specifically for the lowest redshift bin because that is where we have the largest range in sizes. And on the right-hand side, I show you the 3 least aggressive crops. And as you can clearly see, the places where GaMPEN does the maximum amount of cropping is places where it's the smallest galaxies. On the other hand, for if there's a very big galaxy, it correctly learns to make a smaller kind of crop. So essentially, it automatically learns to crop galaxies based on their size without us having to either estimate the size or engineer this in a very specific way. A couple of things to note is that the STN, once it is trained, it can be detached from the main framework. You don't have to use it for morphology classification anymore. You can use it for any task that you have. And the automatic cropping feature of GaMPEN, what it allows us to do is that it allows us to apply GaMPEN to data sets over a wider redshift range without needing to estimate the radius beforehand in any way. So that is hopefully you have now an understanding of how our cropping mechanism works. Next comes the more important thing about estimating parameters and their uncertainties. So with GaMPEN, we estimate two specific kinds of uncertainties. So we estimate epistemic uncertainties, which are essentially uncertainty associated with the limitations of the model that you are using for predictions. Essentially, it's not a perfect model. So you want to estimate those uncertainties, and that is your epistemic uncertainties. And you also have aleatoric uncertainties, which are uncertainties associated with the noise in both your images as well as your training labels. And to estimate parameters and uncertainties, we use our downstream convolutional neural network. So the image, after having cropped, it is passed to this module, and it goes on to predict three parameters: bulge-to-total light ratio, effective radius, and flux. Now, you might think of this as a regression problem, and the natural intuition might be, okay, can we just use something like a mean squared error as a loss function? You could do that, but then you wouldn't end up with any uncertainties. So what we have to do instead of making point estimates, what GaMPEN does is just predicts the parameters of a multivariate Gaussian distribution that is essentially we predict a vector of means for all the three parameters and this covariance matrix. And I should note here that we do the full covariance matrix. We don't do just the diagonal elements. And what this helps us to do is account for also the covariances between the different parameters. And then essentially, if you just write out the log likelihood of the output parameters, then that is our loss function. So if you just write out the negative log likelihood of all the output parameters, this is what we use as our loss function. And this is how we get the estimates of sigma in our models. Now, sigma here represents the aleatoric uncertainty in the predictions. That is the uncertainty associated with the noise in our images or the training data. As I told you already, that we have a different kind of uncertainty that we also need to model, which is the epistemic uncertainty. How do we do that? Now, to model epistemic uncertainties, where we are trying to somehow account for the fact that our model is not perfect, you can think about this problem as essentially, if I write this out, that you are trying to estimate some parameters y, given some training data x, and you're given an image x, and then you have your entire training data d that you trained on. What you need to marginalize over is these different weights. So essentially, you have trained only one network, which has some weights and biases, but you could have trained a lot of different networks, right? But we ended up only one. So you need to marginalize over this. And you can replace this thing. You can replace this PWD. It's, of course, impossible for us to know the entire distribution of networks that could have been present, which solve this problem. So essentially, you replace that with a variational distribution QW, and then this becomes an approximate. You can approximate this integral with a sum. And in practice, what this means is, if you know, you probably many of you have heard about this. What we use is called Monte Carlo dropouts. Essentially, what we do is we take our trained network, and what we do is that we turn off random neurons in that network according to a Bernoulli distribution. So essentially, we feed the same image through the trained network multiple times. And each time we are turning off different neurons. And what is happening, as you can see, is over here, each time it's predicting a slightly different distribution. And now you need to combine both these things. I talked about two different forms of uncertainties, and now you just need to bring them together. And what we do over here, this kind of gives you an overview of the entire process that we use for our training and evaluation. So you have some input images. For these input images, you have your kind of predetermined answers, which you know. You feed them into the STN, which crops it, and then you feed into the downstream convolutional neural network, which gives you the estimate of the mu and the sigma, that is the parameters of the multivariate Gaussian. And based on this, you kind of calculate the loss function, and then you train it. This is during training, or before training. This is while you're training the framework to do different things. Next, once it has been trained, what we do is for every image, we make an estimate of a mu and a sigma. And then the multivariate Gaussian that we're predicting, we draw a sample from it. And then we repeat this entire process 500 times for every image. That is, for every image, we predict 500 different multivariate Gaussians. And from each of these Gaussians, we draw a sample. And this entire collection is what are predicted distributions of the parameters. And this helps us to kind of account for both the kind of uncertainties together in one training set. So hopefully that kind of gives you an overview of how we do the entire training. But how are we predetermining these values for our training set? That is, for our images, how do we know the right answers? And I kind of alluded to this challenge a little bit before, earlier in my talk as well. That is, how do we get training data? So let's say you have a CNN and you have a brand new survey and you want to use images from that survey to come up with parameter values. But if you are using a CNN to come up with parameter values, how do you get your training data? If it's a new survey where the galaxies have not been looked at before. So you kind of get stuck in this chicken and egg problem. So what we do to kind of overcome this problem is something we have been doing for the past few years. So what we do is we first take an untrained GaMPEN framework. We first use simulated galaxies. And by simulations, I don't mean full hydrosims with radiative transfer. We are just making light profiles. So each light profile has two components. It has a disk and a bulge. And then we convolve these with real PSFs and add real noise. And we come up with these simulated galaxies, which we can make. They're very cheap to make, so we can make as many of them as we like. And then we initially train this framework on these simulated galaxies. And then what we do is we take a smaller number, much smaller subset of the real galaxies that we have, and we determine their true parameters using light profile fitting. And this is what we call the transfer learning step, where we take this simulation trained framework and fine tune it slightly based on these real galaxies. And once we have done that, then we can just plug in all the leftover data in our sample and just run it through it to obtain the predicted values of the bulge to total light ratio, effective radius, and flux. So essentially, training on simulations and then fine tuning on the real data allows us to drastically reduce the amount of real data that we need for 1% or even less than 1%, close to 0.5% of the total data that we have. So again, just kind of giving you an overview of the entire sample. So we have 8 million galaxies. We analyze 50,000 of these galaxies using light profile fitting. And then we use 30,000 of them to perform transfer learning. And then 20,000 of these galaxies are holdout galaxies. That is, we have determined the right answers using light profile fitting, but the network has never seen it. So this is all the results that I show you from now on will be kind of on this holdout set. That is, once the network has been trained, we apply, of course, all the galaxies in our sample through it. But for 20,000 of those galaxies, we still have the right answers that we have determined. So we kind of compare to see what a light profile fitting technique tells us and what our neural network is telling us. But first, before I jump into the results, let me just show you some predicted distributions to understand how they look like. And in the 3 rows here, I'm showing you galaxies in the randomly chosen galaxy in the lowest redshift bin, the middle redshift bin, and the highest redshift bin. And the left column is the prediction of bulge to total distributions. The middle column is the effective radius, and the right column is the magnitude. And as you can see, all the distributions that are in this plot, they're predicted by GaMPEN, they're unimodal, they're regular, they look regular distributions, and they also conform to the physical limits of each variable. As you can see over here, for example, the bulge to total light ratio, it's a ratio between 2 parameters, and the denominator is the total value, so it cannot be less than 0 or greater than 1. And as you can see over here in this plot, it cuts off at 1. We don't go on predicting values less than 1. And this we do through some variable transformations, and I won't go into, it's not like I'm like by hand chopping the distribution at 0. This is not what is happening. We essentially have to do a little bit of variable transformation to engineer this into the framework. But as you can, and along with the distributions, I'm also showing you the confidence intervals. So we estimate the 68, 95, and 99% confidence interval, but just by doing an integration over the estimated probability density function. And I will use these intervals to talk about different things coming on. But this is just to give you an idea of how our predicted distributions look like, and how we use them for different things going forward. And also, if I talk about predicted value going on from now, what I mean is essentially the mode of the predicted distribution. So next, let's look at the performance of GaMPEN, how it looks compared to GalFit, which we use to determine our light profile fitting values. And as the three rows here are the lowest redshift bin, the middle one, and the highest one. And as you can see, all our values are kind of close. Most of the galaxies are clustered around the line of equality. And I would point out that I'm using a logarithmic color scale over here. So the lowest bin is just one galaxy. So you do see outliers over there, but most of them are closely kind of centered around the line of equality. And what this plot helps us determine is the values of typical errors. So essentially the typical errors for the bulge-to-total light ratio, effective radius, and magnitudes are kind of shown in this plot. And depending on the nature of your scientific study, this will be more or less should be appropriate for what you want to do. But the entire point of using a Bayesian framework like GaMPEN is that even if you're wrong, then the network should automatically take into account, in the sense that it should predict broader uncertainties in regions where residuals are higher. So inherently, if you don't do well in certain regions of the parameter space, then the network should automatically predict higher uncertainties over there. So what we do to do that is we kind of evaluate GaMPEN's posteriors specifically. And to evaluate the posteriors, what we do is we calculate this thing, which is called percentile coverage probabilities. So essentially what I'm trying to see is that the percentage of times the true value is within a central confidence interval of the predicted distribution. So just to elucidate on this, let's say this is a distribution that I predicted, then 68% of the time, if this is the central 68% confidence interval, then 68% of the time, the true value should be within this most probable 68% confidence interval. And now, if I just show you this plot where on the y-axis, x-axis, I have the different coverage probabilities, and on the y-axis, I have the three different confidence intervals. This is where we expect the theoretical values of these things to lie. And this is what the calculated coverage probabilities are. And this is, I'm showing you only for the lowest redshift bin. And if you see for the middle and the high redshift bins, they kind of all align pretty well with the expected coverage probabilities. And what this is showing you is essentially the distributions that we predict are neither too wide or neither too narrow. They are exactly at the perfect, almost at the perfect level as they should be. And to give you an understanding over the errors, here I'm showing you the mean coverage probabilities, where I have averaged over the three different parameters. But even if you were to take each parameter individually, our deviation is never more than 5%. So this kind of tells you that on the whole, on the average, the distributions that we predict are well calibrated and accurate. Next, hopefully now you have an understanding of what is the typical error, what does the uncertainties that we predict look like. But now the question comes that where are these errors? Are we more wrong in certain parts of the parameter space compared to others? Are we more right in certain parts of the parameter space compared to others? And what I will show over here is these bunch of plots, and I'm just showing you one plot over here, where on the x-axis, I'm showing you the predicted parameter. For example, I'm showing you predicted bulge-to-total light ratio, and on the y-axis, I'm showing you the residual magnitude. So essentially, what is the difference in magnitude between what the neural network tells me and what I determined from profile fitting? And if it's an ideal case that there's no pattern in it, then it should look like this, where it's all centered around this y=0 line. Now, if I just expand this to show you all the three parameters, then you see for both the radius and the magnitude, there's no kind of very strong features. Mostly they're all centered around the line of equality. You do see some features for the bulge-to-total light ratio, which was where, if you remember from the plot before, where we had more scattered compared to the other things. And there are a couple of things to discuss over here. Close to the edges, and we had seen this also in our simulations, close to the edges, what we have is this effect that we call the edge effect. And essentially what happens is that if there is a value which is very close to 0, the network doesn't predict exactly 0, it predicts a value slightly more than 0. On the other hand, if a bulge to total light ratio is perfectly 1, it never predicts 1, it predicts a value slightly less than 1. And therefore, it leads to these like features that you see at the edges. And we had shown in previous work that what you can do is essentially at the edges, instead of predicting the exact value, what you can say is that, okay, I cannot determine the exact value, for example, over here. I cannot exactly determine the value of the bulge to total light ratio, but I can fairly say with confidence that the predicted bulge to total light ratio is less than 0.2. On the other hand, same for the highest. When you go for very bulge-dominated galaxies, you can say, okay, it's hard for me to say whether it's exactly 0.9 or 0.95, but I can say that the bulge fraction is greater than 80%. So essentially, within this range, you can make numerical predictions, and outside that range, you can just stick to making just predictions that strongly disk-dominated or strongly bulge-dominated. On the radius, you see that there's again, with the bulge to total light ratio, that as we go towards lower values of radius, the width, essentially the residuals increase. That is, for galaxies which are increasingly smaller, we are making predictions which are divergent from what we obtain by light profile fitting. And this is not totally unexpected. This dashed line over here shows you where the median seeing is, Hyper Suprime-Cam. And if, of course, you're going beyond seeing or you're very close to seeing, then two different methods, it's not very kind of surprising that they come up with slightly different answers. So essentially, GaMPEN's bulge to total light ratio residuals, they are higher for certain edge cases, and they're also higher for smaller galaxies. But again, kind of the question that, okay, we are doing worse in these specific parts of the parameter space, but are uncertainties also high for this parts of the parameter space? Because if it is working as expected, it should produce higher uncertainties in these regions where higher residuals are present. And this is exactly what is happening. So what I show over here is on the x-axis, I have the different residuals, and on the y-axis, I have the sigma, which is essentially the width of the predicted distribution. And note that we don't expect a one-to-one correlation between residuals and sigma. They should just be correlated. We don't expect like a linear trend over here. And if you run a statistical test of correlation, you will see that all of them are strongly correlated with each other, and you can reject the hypothesis of null correlation with very high, strong significance. So essentially, GaMPEN, what it does is that in the regions where you're uncertain, where your residuals are higher, it automatically goes on and predicts larger uncertainties. And this is what helps us achieve the calibrated coverage probabilities, which I showed you a few slides back. Now, this was all kind of self-consistent. This was training this network and also testing it out on our own data, like where we had ourselves determined different parameters. But there's also some value, of course, to test it out with most of the galaxies, and our sample have not been analyzed morphologically with the bulge twist decomposition before, so we cannot do a very broad comparison. But what we are able to do is compare with two other independent studies, one of them performed with Sloan Digital Sky Survey, and another which is SIMARD, and another which has been done more recently, and that is using a different tool, but again on Hyper Suprime-Cam. And as you can see from the numbers, these are on a much smaller subsamples of our total sample, but still kind of this gives us an idea of what our results are. And what I'm showing you over here are, again, the density plots. And these different error bars, they are not kind of estimating the density in this figure, but what they're showing you is, since we predict full distributions and not point estimates, this is showing you what is the average error that we predict near that point. So that kind of tells you, okay, what do the distributions look like? If I talk about the SIMARD catalog, they kind of more or less within the errors that we predict, they more or less agree over like the bulge to total light ratio, effective radius. We see the slight discrepancy, as you can see in the magnitude, they are a bit off. And we tested these galaxies out by galvanizing them by hand as well. And we do it when we do it separately with SDSS and Hyper Suprime-Cam. We believe that this difference is just due to the fact that we're using two different imagers with two different filters. And that is why there is this, it's a 0.15 offset between the two magnitudes that we determine. When we compare it with a similar study done on the same kind of similar data set, Hyper Suprime-Cam, but the difference, major difference with this other study is that This was done using a single component Cerseic fit, so we don't have estimates of bulge to total light ratio. We have to compare it with Cerseic index. And Cerseic index and bulge to total light ratio is a very complicated correlation. It's not a linear or not even a very simple correlation of how they should be. But generally speaking, higher Cerseic indexes should have higher bulge to total light ratio. As you can see, again, this is what we see in our data set. And if you compare the effective radius and the magnitudes, again, within the uncertainties that we predict, they roughly agree. So essentially, our prediction algorithms, they largely agree with other work, which has also been done using more traditional methods for smaller subsamples of overlap. So this is kind of telling you, okay, that this works. This is an entire data set and can produce robust uncertainties as well as parameter fields. Now you next come to the question of what are we doing? What are we doing with this morphological catalog of 8 million galaxies that we have right now? So we're primarily looking at 4 different things. So we're looking at the buildup of mass and size. We're looking at the shutting down of star formation, the influence of environment, and the influence of aging. So these 4 different things are what we're looking at right now with this specific catalog. And I don't have time, of course, to go into all of them, but I will show you just a little bit of a example of the kind of things that we want to do. For example, what this shows you is the color mass diagram at the middle and the highest redshift bin. And what we have done is split the sample by the disks are over here, which are disk dominated, I should say, and the bulge dominated galaxies are over here. And if I just forget about the high redshift bin, just focusing on the mid redshift bin, what you see over here is for the disks, you see this gradual, it's a much more gradual change in mass. It kind of increases as much, it seems, until it reaches a critical mass where it kind of quenches a little bit more rapidly. On the other hand, for the bulge dominated galaxies, we don't see such a trend. Instead, after being formed, it seems to quench rapidly through the green valley into the red sequence. So essentially, this is kind of all bringing it back to earlier when I was talking about how we can use morphology to kind of trace out these different evolutionary pathways and mergers histories. And this is the kind of work that we are doing currently with this morphological catalog. And if you have ideas about different things that you would want to do or want to collaborate on, I'm more than happy to talk about that. So kind of summarizing everything specifically about GaMPEN, the software paper is already out there on the archive. The specific catalog should be out there in October. The entire code, along with the trained models and tutorials, everything will be public. But if you want to use it before that, please don't hesitate to get in touch, and I will be more than happy to talk to you. Thank you so much for your attention.
Great, thank you, Aritra. We have time for questions, if people have any. While people are thinking, the question I wanted to know is, applying this to 8 million galaxies, how long does that take?
So 8 million galaxies, it took us running it on about 5 or 10 GPUs. It takes us about like 3 or 4 days of roughly runtime. That is how long it takes. But the main challenge that we've kind of interfaced when I was doing this was having just so many individual files to deal with. So the runtime was often not the problem, but just interfacing with such a large number of files that ended up being a challenge for us. But in terms of rough runtime, if you just have, so a good way to think about this is we have 8 million galaxies. We are doing 500 evaluations for every one of them. So we are very close to a billion or more than a billion kind of, once I've trained the framework, that is the number of pass-throughs I need to make. And each one takes close to a millisecond or less than a millisecond. So that's the runtime that you have. So it's, in terms of runtime, we don't have that much of a problem.
Good, thanks. Yeah, that's really interesting. Anybody else have questions?
Yeah, I have a question. That was a nice talk. Thank you so much. I was wondering if we can use real galaxies, those from Hubble observations from HST, to just training your model. It's possible, yes, for example, use the I-band data and degrade them to what you will be see in Subaru, and then use them for training your model.
Yeah, so essentially these GaMPEN, you should be able to train it with space telescope data as well, whether it is Hubble or JWST. We are kind of trying we are doing this right now with Sears data from JWST, but with Hubble, and we have trained with the GAMRNet framework, which is the classification instead of the parameter estimation framework. There you will find already trained models available from us, which work on candles data. But with GaMPEN also, you should be able to just take it, just train it on any data that you have. You just have to remember that if you are applying it on you can't take our trained model and directly apply it on Hubble data because it looks different, of course, from Hyper Suprime-Cam data. But if you do sort of transfer learning, a little bit of fine tuning, then you should be able to use it without any problems.
Okay. And also my other question is about the performance of the GaMPEN about just deblending sources. Have you just tried to look at the performance of the model to deblend some of the sources, especially in the deep data?
Yeah. So there are two kinds of, and maybe I have I don't have a backup slide about deblending, but essentially the kind of two challenges that I did not talk about are mergers and irregular galaxies and blended galaxies. So with mergers and irregular galaxies, what we are doing is we are using this tool. Michelle Lochner has this tool called Astronomy, and I'm working with with a master's student here at Yale who is applying Astronomy to kind of pick out merging and irregular galaxies from the sample and see what GaMPEN is doing for them, and then we want to kind of mark them out in our produced catalog. In terms of blended galaxies, there it's a little bit more challenging in terms of Hyper Suprime-Cam at the redshifts that we are looking at. We expect like maybe 10% of galaxies to be blended. And Hyper Suprime-Cam has a parameter called the blendedness parameter. So they run an algorithm and they come out with an estimate of how the blendedness is. So our recommendation is to not use our catalog for galaxies which are blended more than where the blendedness parameter is more than 8 to 10%, because there you won't get robust answers. But what we are doing right now is I'm kind of talking with Peter Melchior, who has this code called Scarlet, which does deblending. And the problem is sticking something like Scarlet into a deep learning framework might not work because essentially you need your entire framework to be differentiable. That's the major kind of challenge over there. But if you can make it differentiable in any way, we are kind of seeing whether we can put on a deblender kind of at the front load, just we are doing the cropping so that it can do the deblending itself. But for now, the recommendation is to ignore our predictions for very highly blended galaxies.
Thank you. Thank you.
I think Francois has a question.
Yes, thank you. I'm curious about the influence of the variability of the seeing, which I'm not sure if I missed it, but I don't think I heard you mention it. You say the median seeing with the Supreme camera is 0.85 arc-second. Presumably the best ones are half the amount, and the worst, there's no upper limit, but let's say a factor 2 up. Do you eliminate some of the images based on too poor or too good seeing? Presumably not. Or have you studied how the seeing of individual images may affect your results?
So the only way it shows up in our data is our residuals increase when we get close to the seeing, as I kind of showed in my one of the slides, that when we get closer to the seeing, the estimate of the bulge-to-total light ratio, that gets a little bit wobbly. So that is the kind of effect that there's obviously, we are having an effect on if I have something very small, which is close to the seeing limit, then we are, our residual. We have not done till now is taken like a range of galaxies with different seeings and make the same, like we have it in our data set, but we have not studied the exact trend that is over there. I expect that there will be a trend, but we have not done that specific study till now.
Okay, thank you.
And Maddie, you have a question?
Hi, can you hear me? Awesome. Yeah, so about the transfer learning, when you were using those synthetic data to just, for your training. So do you see any improvement if you were using some galaxies from simulation, like from hyper simulations, rather than just modeling the light profile?
So are you saying that instead of doing the first step, which we're using simplistic light profiles, instead of that using full radiative transferred images, right? Did I get the question correctly?
Yeah, correct. But yeah, so right now you're just you're not using any kind of simulation like embodied simulation at all, right?
No.
Yeah. Yeah, so if you were just doing not necessarily radiative transfer, just post-processing the embodied simulations or hydro simulations. So do you think that you would get any improvement if you were using that instead of just simple model for the light profile?
So I'm not very sure. That's an interesting thing to do either way, whether kind of I am hesitant to say that it will have an improvement on the final thing, because I think what has mattered for us is that transfer learning in the between. And what we have found out typically is that these neural networks, even if there's a slight shift in domain, like you might make a hyper realistic simulation, but if it's not the exact same data from the same telescope, it will freak out. Because there's these minute differences in pixels that it picks up on. But what you're suggesting, Mary, what that would be interesting for is, of course, it might be interesting to just do this exact same thing for hydrosims themselves, that you might be able to use these frameworks to just study the morphologies in hydrosims and look at what they are. And it would be an interesting test to see whether there is kind of a benefit in replacing that first step of training with a full hydrosim. And it might be I don't think the end result would make even accurate predictions, but what might happen is you might be able to get away with transfer learning, like we use 0.5% of a sample of transfer learning. But if it's full hydrosims that you're training on initially, that fraction might decrease to like 0.1% or even lower than that. You might be able to make the jump to real data with even lesser transfer learning that we are doing right now.
I see. Yeah, that makes sense. Yeah, thank you.
All right, I don't see any more questions. So I just want to remind everybody that Aritra will be visiting in person on October 19th, right?
Yes.
That's the right date. So I will, closer to the time, I'll send out an email reminding everybody and with times to sign up to meet. But for now, let's thank Aritra again for a really interesting talk. And thanks everybody for joining us today.
Thank you. Thanks so much, Andrew.
Great. Thanks, Aritra. Really nice work.
Thank you.